Chapter 6, Electricity and Magnetism. And we're going to start with electricity and then go to magnetism. Basically what is electricity? Um, it turns out that it's actually moving charge. So you probably learned, very early on that an atom is, has a nucleus, and inside the nucleus there are protons, which are positively charged, and neutrons, which don't have a charge. And then around the nucleus, in some manner, there are electrons, which are negatively charged. And really, electricity, for the most part, has to do with the movement of electrons. Um, and yeah, so uh, let's take a look at it. So when an atom has the same number of protons as it does electrons, it's neutral. And then when there's like an extra electron, that would be negatively charged. If there's too few electrons, like in this situation, then it would be positively charged. All right, and so yeah. All right, and let's see. So there's this thing called electrostatic charge. It's the kind of thing that happens, for example, when on a winter's day, you walk across a carpet and you through friction between, let's say, your feet and the carpet, you build up some static charge. Either electrons are leaving your body or electrons are going into your body. It doesn't really matter which. But in that case, there's an electrostatic charge. And when you touch a piece of metal, that gives a path to what's called ground. And once ground occurs, once ground is seen, if you will, by the electrons, they will move. Either from ground to basically fill up the excess protons in your body, in the case of this example, or they'll go into ground if there's too many electrons in your body. All right, and let's see, what else do we want to talk about? There are, of course, conductors. Usually we think of metals, for example, as a conductor. There are insulators. A great example would be plastic. Are really good examples of insulators. Glass and wood are also insulators. And then there's this thing called a semiconductor. Silicon, the element silicon and germanium are really good examples of that, where the atom can be forced to act either like a conductor or like an insulator, and those are used all the time nowadays in modern electronics. They're basically little switches that can be turned on and off. If you just kind of think of computers, they have zeros and ones. They speak that language, the binary language of zeros and ones, and having electronic devices that can be on or off. That's basically representing a 0 or a 1 in computer chips. All right, so here's our first equation. Charge is measured in units called coulombs. Well, here's the equation right here. It's very simple. Charge is represented by this lowercase q. E is the charge of a single electron, and N is the number of electrons. So what this equation means physically is that there can be, let me make sure that N is just a whole number, a positive whole number. So N could be 1, it could be 2. So you could have one, if you have the charge of one electron, N is equal to 1, and the charge, Q, would be equal to the charge of one electron, which happens to be negative 1.6 times 10 to the minus 19th coulombs, as it shows right here. Okay, so that's the charge of a single electron. Of course, I don't know, for some reason they forgot to put the negative in right here, but it is negatively charged. So usually what we're doing with this equation is we're solving for Q, or we're solving for N. You have a certain number of electrons, what's the charge? Or conversely, if you have some charge, then you could figure out the number of electrons. Now it turns out that this E symbol in this equation is actually for both electrons and protons. If the E is negative, then the charge Q is negative. If the E is positive, it's actually the same numerical value, 1.6 times 10 to the minus 19th coulombs, but then you're talking about protons and not electrons. So this value, 1.6 times 10 to the minus 19th coulombs, is called the fundamental charge. And to this day, we have never seen a charge in nature that is smaller than that number. It's a very small number, notice. I mean, 1.6 times 10 to the minus 19th means, you move this decimal place 19 places to the left. And so this is an exceedingly small number. All right, so let's do a quick example, All right, for our first example, we're going to let, remember we're using this equation, Q equals some number, where N is just a positive whole number, times the charge of either an electron or a proton. And if the charge is negative, then we use the negative value where, E is plus or minus 1.6 times 10 to the minus 19th, that's a 9, coulombs. All right, and so let's do a quick example. Suppose we had, I don't know, say N was equal to, let's say 5,000, just to make it simple. Then if that's the case, what's the charge? And it's 5,000, let's say, electrons. Okay. And so if it's electrons, then what we do is we choose the negative value. Let me circle that. So we choose the negative value. And so Q is 5,000 times negative 1.6 times 10 to the minus 19th coulombs. All right, or let me put parentheses so that doesn't look like a subtraction problem. All right, so let's put this in our... So the value that I get when I do this calculation is, let's see, what did I get in my calculator? Here it is, negative 8 times 10 to the minus 16th coulombs. All right, so there's our first example. Let's do it, and much more commonly, we're going to not know N. N will not be known, and will be given some charge. So here, let's do another example. Suppose, so here's our next example. Suppose that Q is, I don't know, how about 1.5 times 10 to the minus 11th coulombs, and we want to know what N is. So what's N? What's the number? I'm going to make a capital N, but it's the same thing as a small n. So what's the number of protons, right? That's what we're solving for. Why is it protons? Because this is positive. It's a positive charge. So we want to know the number of, in this case, protons. Okay? This should be an O. All right, so with positive, well, let's just solve the equation. Okay, so Q equals N times E. So N. I'll stick with the lowercase. I shouldn't have used an uppercase. So N is equal to, well, it's Q over E. Okay, and so since this is already in coulombs, we can just put that in there. So it's 1.5 times 10 to the minus 11th coulombs divided by the charge of a single proton, which is the same as the charge of a single electron, but it's positive, 1.6. Remember, this is the lowest charge that can exist, times 10 to the minus 19th coulombs. And so the coulombs cancel, and let's see what n is. Alright, so when I put it into my calculator, I get this very large number, and it's actually not in scientific notation on my calculator here. I get like 9,375, and then there's 4 more zeros after that. But so I'm going to count the zeros in threes, so I go 1, 2, 3, and then 1, 2, 3, and then one more. So it's 9.375 times 10 to the 7th protons. Okay, so that's the number of protons that make up this charge. Right, and so it's always a whole number of protons, and of course this is a whole number. It's a very large number, but it's always a whole number of protons or a whole number of electrons. Alright, so let's do at least one more example here. Let's say now Q is negative 425 microcoulombs. Notice we have the symbol micro here, right here. And micro is, of course, a metric prefix, and so we really can't use that in the calculation, so we need to change micro into a numerical value. So it's negative 425, and micro, if you remember, means times 10 to the minus 6th. So that's the way that we need to put this in our calculator, times 10 to the minus 6 coulombs. All right, so don't forget these metric prefixes. We have to, write them as a numerical value. Okay, so what is the answer? It's going to be, n is equal to negative 425 times 10 to the minus 6th coulombs divided by, now we're going to use the negative, which is of course the charge of electrons, so we're going to find the number of electrons that form this charge, 1.6 times 10 to the minus 19th coulombs, and the answer is, let's calculate. Alright, so I put this in my calculator. Notice, of course, these negatives cancel. You always get a positive whole number, so I've rounded this to 2.7. It's like 2.65 or something like that. But 2.7 times 10 to the 15th electrons. Right? They are electrons because the original charge Q was negative, and so it's electrons. Only electrons can make up a negative charge. All right.